Good morning, everyone, and thank you for joining us. We're really fortunate today to have two distinguished statisticians presenting the materials on Bayesian applications. Dr. Jose Ramirez is the chief statistician in the Quality Data Sciences Group at Amgen. Jose received a licentiate degree in mathematics from the Universidad Simon Bolivar in Caracas, Venezuela, and MS in applied statistics and PhD in statistics from the University of Wisconsin-Madison, where he was one of the founding members of the Center for Quality and Productivity Improvement. And prior to Amgen, Jose was part of the Quality and Reliability Group of the Semiconductor Division of Digital Semiconductor. Jose had worked closely with engineers and scientists to promote statistical thinking. And I'm pleased to also introduce Dr. Feng Chen, Director of the Analytical Software Development at SAS Institute and a fellow of the American Statistical Association. Feng manages the development of statistical software for SAS Stat, SAS QC, and analytical components that drive SAS visual statistics software. Also among his responsibilities is the development of Bayesian analysis software and the MCMC procedure, the flagship Bayesian procedure in SAS software. And before joining SAS, Feng received his PhD in statistics from Carnegie Mellon University.
So good morning, good afternoon, and good evening, depending on where you are on the planet. And welcome to our webinar of Bayesian applications in CMC. Feng and I are very, very excited to share with you some of the applications we have been working on. But before we start, I have a confession to make. I'm not a diehard Bayesian. When people ask me what I do for a living, I tell them that I help people make sense of data and the claims and decisions. Hello?
No,
yes.
I'm a diehard Bayesian, that's all.
I know. And the claims and decisions that come along with that. So from that point of view, I'm more of a pragmatist. But over the years, my my appreciation for the value and the power of Bayesian methods has grown. I was fortunate that I was exposed to Bayesian statistics very early in my career. In my senior year in college, there was a professor that just came back from Imperial College where he did a dissertation on priors for linear models and transformations. So he taught us a little bit of Bayesian statistics. Later on at University of Wisconsin-Madison, while I was working in the statistical lab, I suggested that we use Bayesian methods for a problem that came in. And what do you know? My first publication, a technical report, was on using Bayesian methods for monitoring groundwater quality. But back then, we did things by hand using conjugate priors, and we can derive the formulas. So it's a little easy. But in my experience, a lot of us, tend to think that Bayesian methods are somehow complicated. And I believe a lot of that has to do with software. Because if you work in industry, you know that if it's not easy to implement with software, it's very likely that you're not going to use it. You may go to a conference, see something, very excited, and then we don't have the time sometimes to do it. So when PROC MCMC came out, and full disclosure, I'm totally and completely biased towards SAS that I've been using for all my professional career, even in grad school. That was a game changer, and I've been fortunate. Actually, it's a privilege for me to be able to work closely with the brains behind PROC MCMC. And today, you are fortunate too, because Feng Chen, which is, as he said, the true Bayesian of the pair, is here with us, and he's going to share not only all his knowledge and wisdom about SAS procedures, but also about Bayesian techniques and methodology. So, what we are going to do, is talk a little bit about some of the things that we're going to be covering in this 4-part series. Today, we're going to give you a little bit of Bayesian basics, so to set the stage, to give you a common lingo, because we may all have different ways of describing things. And if you're not a Bayesian, then you get a little exposure of what Bayesian statistics is about. Then we'll talk about some of the problems that we may face in CMC, for which we have used Bayesian statistics, like setting acceptance criteria, evaluating comparability, and the core of this will be using prior knowledge, all this historical information that we are very lucky to have in biotech that we can use to our advantage. And then the second part of today, Fanny's is going to give you an overview of the two PROCs that we use for these applications, PROC MCMC and BGLIMM. For Bayesian Basics, we're going to talk about statistical inference, because that's at the core where, there's differences and commonalities between frequentists and Bayesians appear. We're going to talk about the Bayes rule. We're going to have a little fun with an example from Professor Efron, the twins challenge. Some of you may be familiar with that. It's a sample size of 1, but it allows to show you how the Bayes theorem works. We're going to discuss Bayesian inference, how to choose priors, and then some of the advantages and disadvantages of Bayesian methods. So statistical inference. All of you that are out there that are statisticians, you know that our job is to make some claims, as I said, for a population based on a sample. So we go from the sample to the population inference. And surprising to me that these days of big data, for those of us in CMC, things that our data sets are getting smaller and smaller. So this issue of making inferences for a sample is important. And you'll see throughout this webinar series how we can use this prior knowledge to help with the inference. But as I also mentioned, you will help the people we work with, that we collaborate with, in terms of uncertainties. They have to make claims, they have to make decisions. Will this lot pass? Will the post change will be similar to the pre-change? Is this biosimilar comparable to the reference product? And people have to make decisions using the analysis. And for that, we need to be able to communicate these uncertainties so they can make more informed decisions. So the way of doing that, we have two philosophies. Most of us are frequentists, and there's also the Bayesian one. And unfortunately, we tend to think that there are competing strategies. But actually, I refer you to this paper by Professor Box back in 1980, and he doesn't see these two things as competing, but as complementary. And he talks about criticism and estimation as functions that we play during data analysis, and how these two play an important role. So here we have a little diagram to summarize how we view the frequentist statistical inference. We have some data, we have some quantity of interest that we want to estimate from that data, and then we have a likelihood. And that likelihood is a probability distribution. I put normal in quotes because that's what is normally used, pun intended. Yeah? And then we have a procedure that can be a statistical interval, a significant test, and then with that, we make some type of inference. Yeah. On the Bayesian side, you'll see that even though people think that they're competing strategies, we share things in common. We still have the data, we still have the quantity of interest, and we still share the likelihood. And the likelihood, again, is a probability distribution. And I took out normal there because the Bayesian methodologies give us the enormous flexibility to use almost any type of distribution. I know what you're thinking. Yes, within the frequentist framework, we can also use different distributions with generalized linear models and generalized linear mixed models. But in general, the tendency, especially for practitioners that are not very familiar with the statistics, is to use a normal distribution. So in Bayesian statistics, we also have another distribution. This is a prior. And this seems to be the contentious point here, because we have to talk about the probability distribution that is somehow subjective. But we tend to forget that this probability distribution here is also subjective. But in the frequentist point of view, we seldom talk about it. And I think it's because, everybody assumes that the data is normal. Yes, we do some checks for that. And in software, any type of statistical analysis that you do behind the scenes, you're assuming that the data is normal, but that's not necessarily a valid assumption. So this issue of being objective and subjective, we're going to discuss that. So just keep that in mind, that even if you're doing frequentist statistics, there is an element of subjectivity in there. Now we have two probability distributions now to deal with. How do we do inference with that? Then that's where the Bayes rule comes in, and that allows us to combine these two probability distributions into what we call the posterior. And the posterior is a combination of the prior and the likelihood of the data. And then all the inferences in Bayesian methodology are done using the posterior distribution. And the Bayes theorem, the Bayes rule, is that simple formula. It's hard to believe that it's almost 260 years old. And it's a simple formula. A lot of you may remember that from your probability classes. And this is just a theorem that relates conditional probabilities. You have the probability of B given A, and here you have probability of A given B. So you see how the Bayes theorem switches things around. So it allows to combine information and play, if you will, with conditional probabilities. And this is the basis of the Bayesian statistical inference. And to quote Professor Efron, it's the first serious triumph of statistical inference, but it's treated with suspicion by most statisticians. And we hope, Fan and I hope, that by the end of this series, we can lift the veil of that suspicion and you become more comfortable with Bayesian techniques, and you can see, as I've been developing over the years, appreciate the value and power of these techniques. But in essence, what we're doing here is we are combining or connecting the posterior beliefs that they're proportional to prior beliefs, okay? And we'll explore that theme as we go on.
There's a couple of things I'd like to add.
Yes, go ahead.
To enhance what Jose was saying, is that the switching of the probability was a very contentious point through the history, because we started with something describing what the data look like, and what we want to infer. So when we think of a probability of A given B is describing what the data generating mechanism is, giving some unknown parameter. And the switch happens is we want to say, given what the data tell us, what can we say about the parameter? And often this sounds very conspicuously sort of naive, and it's typically how would people do inference. You're giving me the data, I want to infer on the parameter. But the Bayes theorem formalizes that thinking, and sort of mathematically, in the sense that it required by that it required a distribution on the parameter. That's where the prior on B comes in, and this became, you're binded by this limitation. So if you are to do a Bayesian analysis in order to do this switch, at all, you have no choice but to go with the prior. Even historically, people like Fisher, they would do inference using the way given my parameter, unknown parameter, and have the data generating mechanism. I want to say something about the parameter itself. It's a switch. But they want to do the switch without having to commit to a prior distribution, or the necessity of having to specify prior distribution. So that's the slight difference. But from a Bayesian perspective, because the reliance on this Bayes theorem, we have sort of no choice but to adapt this prior and embracing it. And this is what Efron referring to, that because of this, the necessary, you must specify a prior. That is the part that's being treated with suspicion by many statisticians. So that's one I want to add to this part.
Thank you, Fang, and that is true. And again, as I mentioned, we hope that we can ease some of that suspicion by showing you how this works with real examples within CMC. And as I was saying, we're going to have a little fun. We're going to see how the Bayes theorem works in practice using a challenge that Professor Efron had. So he was at the student union, Stanford, and with his physicist friend, and she was expecting twins, and she told him that the sonogram showed 2 boys. Yeah? And that's a little piece from that paper. He describes this example, this challenge in several papers for this first time it appeared. So what she wanted to know, because Professor Efron, being the statistician, that's the person you talk to, if you want to figure out the chances that the twins are identical as opposed to fraternal. So what Professor Efron needed to figure out is the probability of the twins being identical given that they are boy-boy. And that's a conditional probability. So you can see right there, probability of identical given boy-boy. So having a conditional probability means, we can use the Bayes theorem to figure out what that conditional probability is. So what do we know? We know that the sonogram showed 2 boys. We know that identical twins are either boy-boy or girl-girl. We also have a piece of information that the doctor told his physicist friend that 1/3 of all twins are identical, okay? So you can see this is a prior knowledge. We also know from genetics that if the twins are identical, the probability of them being boy-boy is 1/2, or the probability of them being girl-girl is 1/2. So we have these 2 pieces of prior knowledge. The information that 1/3 of all twins are identical, and the genetics that implies that the probability of boy-boy, given that they're identical, is 1/2. So what we need to know is the probability of identical given boy-boy, because that's what the sonogram show, and we can use the Bayes theorem. That's right there. And we can write out the Bayes theorem, just essentially the probability of being boy-boy, just expanded to 2 components. But you can see that we already had some piece of information because we do have the probability of identical. We know that that is 1/3. And we also know what the probability of being boy-boy given identical is. That's 1/2. So we have those 2 pieces of the equation. But we can figure out the rest because, the probability of being boy-boy given fraternal is 1/4. Probability of being identical, they told us, is 1/3, but that means that the probability of being fraternal then is 2/3. If you put all those 2 pieces together, then you got the probability of being identical, given that the sonogram, the piece of data show that they're boy-boy, is 1/2, equal odds, okay? This, again, this is based on the prior information that the probability of identical is 1/3, and that's key in this analysis. So if we use the prior knowledge that we have equal odds of seeing fraternal or identical twins if your sonogram shows boy-boy. Same applies if the sonogram shows girl-girl. So what we have is a sample size of 1. We just have the sonogram that showed boy-boy. We have the prior knowledge. The doctor said that the probability of identical is 1/3. Genetics says that the probability of boy-boy given identical is 1/2. And the Bayes theorem allows to calculate the odds as 50-50. And this is the interesting part, and it made me laugh when I read this, because even someone like Professor Efron, which is a renowned statistician and Bayesian, his friend was disappointed because she thought that he was guessing, He just told him the odds are 50-50, That's the flip of a coin. But under the prior information, That is the answer that the Bayesian methodology gives. And then you can see this is also from that paper. The twins were fraternal. So you can see how you can use Bayes' theorem even with a sample size of 1 if you have that prior information. And as Fan was saying, we need to specify that prior, and bring it into the rule. So let's talk a little bit about Bayes inference. In Bayes inference, now we are based on slightly different definition of probability. If you're a frequentist, you think in terms of limited frequencies. You're repeating. If you repeat the experiment many times, then you expect your probabilities to converge to that value that you're getting. But in Bayesian statistical inference, the probabilities deal with a degree of belief.
Yeah, this is one of the most contentious point, I think, of how the Bayesians are defining their probability. Is what is the probability is how likely you personally believe some event is going to happen. It's a degree of belief, and your degree of belief and my degree of belief can be different. And in fact, they are very different. Whether that is, is something that you would want or not, what the Bayesian tend to think is that that's just a way of life. An example of it is we as practitioner statisticians, we look at the same data, but we don't reach the same conclusion. And a reason for it is because we each bring our own different prior opinions on same type of analysis. And the Bayesian just reflects this type of thinking. And as a scientific community as a whole, the job is to each bring their personal belief on a certain probability and communicate and reach consensus. So regardless of that, one point we like to make is that the probability, this is a weird concept to think if you are not familiar with what probability is. It's not limiting frequency. And the reason it's not limiting frequency is because a Bayesian paradigm does not assume repeating of experience. So there's no, you can't define probability from that way. And there are many consequences because you don't define probability that way. It leads to different type of inference. So that's what I want to add.
Yeah, and to add to that, I think that in this way the Bayesians are a little more honest. As Fan was saying, we can forget about Bayesian for a little bit, and we can have the same problem, but we may approach it in a different way. I can see a problem as a mixed effect problem, and some other person may see those effects not as random but as fixed and treat the whole thing as a fixed effect model. So we're bringing our experience, what we believe this particular factor may represent in an experiment. One of the examples is operator. A lot of times people, if they're doing a measurement system analysis, they think of operator as being random. But if you're just working with a lab and you only have 3 operators and you're doing the study in all those 3, that's it, that's your population, then you may think of treating them as fixed. So again, we'll talk about this later too. You have to bring the context to in place here. So this is a sticky point, the definition of probabilities. But behind that, the idea of the beliefs and assumptions that we have, even the frequentists, we do not escape from that. But one of the things that is important to note that gives a lot of strength to the Bayesian inference is this communication of uncertainties. Remember that when we do inference and we work with people, we collaborate with scientists and engineers and help them make decisions. One of the roles that we do in statistics is quantify and communicate uncertainties. So here, this is done through probability statements and via posterior densities. And the probability statements are intuitive. They mean what they mean, not like in the frequentist case that people tend to think that they mean this, but we have to go and explain, well, it's not really that, it's blah, 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 and creates confusion, okay? So from the Bayesian point of view, Bayesian inference is based only on the current data that we have. So that's the posterior of the parameter given the data. That's that conditional probability. So that's the data x1 through xn. The frequentist, on the other hand, assumes that the future data behave the same as the given data. That's the likelihood probability of x given the parameter theta of interest.
This is the nature of repeated experiments, because in the frequentist approach, the likelihood, in fact, well, it's not likelihood per se, it's a sampling distribution. The assumption is you will see similar data many times in the future. You just haven't seen them. Now this boils down to the definition of probability. That's frequency. That's where the frequency comes in. And remember, there's two random variables in play here. One is your data x, and when the parameter theta. And from a frequentist perspective, theta is fixed. So the only thing that can vary is x. And how you're going to vary x is you will see many more data. And if you make such assumption, nice things happen. It's called asymptotics. Asymptotics is if your n go to infinity, things become normal looking, your MLE behaves a certain way, and your tail goes down, etc. And the inference, then you pull back to plug in the current value of the n. But from the Bayesian perspective, there's this thin red line that separates the n from n plus 1. N is what we have observed. N plus 1 is what the future tells us. We don't know. And from a Bayesian perspective, they don't particularly care. And the inference is entirely based on whatever the observed data has been. So this is the line that separates the Bayesian inference from a frequentist-based inference. Is that? And as we see more data, yes. So this is what that means.
And that assumption, I was going to say about this assumption, and we'll show the next data in the next slide, is that sometimes we don't think about this, but some of you may think of Dr. Deming's distinction between enumerative and analytical studies. And here, the assumption that the future data behaves the same, behind that is some type of statistical state of statistical control in the data generation mechanism. Because if we're going to make inferences, if we're going to make claims, predictions about the x1, 2, n plus 2, all the way to the future, then if we have data that does not behave like the one we have, then all those claims and probability calculations are probably not that accurate. So we have to keep that in mind. And sometimes in my experience, that doesn't get discussed a lot. So we just assume that the future data behaves the same.
Yeah.
So what happens if we get a new? Yeah. Go ahead.
To add on to that point, this is really where the assumption comes in play, because in some cases, this is very much true. Like if you are in agriculture and you do a split plot and you're going to grow stuff, and it's probably very likely it's a defendable assumption that you just haven't observed the data yet. Once you see them, then it's perfectly fine. Possibly in population identical fraternal twins, etc., and so on. But in some situation where whether a drug interacts with a human, or how it interacts with a human, or a weather system, a tornado system, would they repeat many times of the similar things in the future, is more difficult to defend.
Yes.
So the Bayesian just say, we don't really want to defend that assumption. If you are willing to, and if it holds, then this does provide a very efficient way of doing inference.
Yeah.
But the Bayesian moved away from it, just say we only concerned what data we've seen. That's it. So.
Yeah. And to be fair, that also happens in manufacturing in biotech too, because that's the reason we have, process controls and process engineers, and we make sure that our processes produce something in a consistent way. That's kind of like the state of statistical control I'm talking about. In those situations, then all this works. But again, if we have a new observation, and this is where you were going to,
right,
Fang.
Right.
So if we have a new observation
we have new observations, then the Bayesian would update their inference because we've seen more data. So if you've seen only 3 data points, your uncertainty will be greater because you are not sure what your theta would be. You have only 3 data points to tell you. But is the data more and more and more coming in, then your uncertainty becomes less and less. But it nevertheless is an exact distribution, but the shape of distribution will change. And that's what and you use that distribution P of theta given X of however many N is to do your inference. And Bayesian is true to that in all situations.
And I think this is what makes it attractive as an adaptive procedure. And that's why I believe the FDA is allowing some of the Bayesian methodologies to be used in clinical trials and all that. And part of that has to do with this. You're learning as you go and you're updating your predictions and uncertainties based on the new data. So again, just keep that in mind that even if we get a new data point, for the frequentist point of view, we're assuming that the data behaves the same. And this goes back to that assumption of the likelihood. We're assuming for a lot of cases that is normal, but that may break down. What if happens if you have an outlier? Or what if, if you remember the market crash and the black swans and Professor Taleb talking about, fat tails distributions and all that. Your probability calculations change if you assume that the data follows a normal distribution or follows a Cauchy distribution. Again, I think the Bayesians are a little more transparent in the assumptions and beliefs that they have that we are sometimes. Okay? So let's talk a little bit about Bayesian estimation. For a frequentist, we normally report the maximum likelihood estimator or the method of moments of a parameter. If the mean would be the average of standard deviation. Now the formula, in the Bayesian approach, we tend to use the posterior mean, which is that expectation of the parameter given the data, as Fang pointed out, with the posterior, so it's that integral here. This is the posterior distribution of the parameter given the data. Now that I've seen the data, what is the posterior distribution? This is the output from PROC MCMC, and Fang will talk a little more about this. And in the webinars 2, 3, and 4, we're going to walk through examples, and we're going to show you the annotated code so you know where things are coming from. But this is just to show you the output that shows that mean there is the posterior mean. Sometimes we use the mode, and the mode is, in my experience, and Fang may correct me here, the mode in a Bayesian analysis is what comes closer to the MLE. It's closer to the MLE than the posterior mean. And yes, sometimes we also use the posterior median. Yeah.
The reason is because the posterior distribution often is very similar to the likelihood function. So you're maximizing the posterior is similar to maximizing the likelihood. But Bayesian, because of the distribution and in the past 30 years, the widespread use of Monte Carlo methods tend to stay with posterior mean as opposed to be making inference using posterior mode as an estimate. There's some other additional, they call it the loss function, utility function associated with why posterior mean would be a good estimate to have. But from a practical perspective, because of Monte Carlo, people tend to use posterior mean mostly in reporting the most likely estimate, the most likely value that we would like to see from Bayesian.
Yeah, the central tendency of the distribution. In terms of the intervals, there are 2 types of intervals here: the credible interval, which essentially equal tail intervals. If you specify 95% will be 2.5% on one tail and 97.5% on the other tail. And a highest posterior density interval in HPD. This takes a little bit of time to digest and understand, but you can think of it as the last bullet. There is the smallest region with 95% probability of most likely values. And this is a true probability. You can say that, yeah, there's a 95% probability that the parameter is going to be within that interval. And this is completely different from the interval interpretation in a frequentist framework. And that, again, that would be the output from PROC MCMC. And you notice that gives you both the equal tail interval. This will be the credible interval, and this is the HPD interval here.
Just to make sure that people understand the difference between a confidence interval and the HPD. A confidence interval is a realization, so it's a function of the data. And the confidence interval is, what the confidence interval essentially says is if we are to repeat the experiment many times, the 95% of the realized confidence interval will trap the true parameter value. But for a particular one, you can't really say what the probability of the parameter is in that or not, because the confidence interval reflects the sampling uncertainties on the data. But a Bayesian HPD interval is a interval of probability statement on a parameter. That's why they say in a Bayesian, you can say that the probability of the parameters in this region or this interval is 95%. That's the reason. The random variable is the parameter, not the data.
Exactly. Yeah. Exactly. But in the frequentist case, you cannot say that. It's like a game of poker. There are probabilities for any given hand that you may have. So before I deal the hand, you know what the probability is that you may get 2 aces. But once you have the hand in your hand, you either have it or not. It's the same with the interval. The probability of the mean being there is either 0 or 1 once the interval is calculated. So the confidence from the frequentist point of view is more like a yield statement on the process of generating confidence intervals. You can think of a manufacturing process that produces confidence intervals, and the yield of that process is 95%, meaning 95% of those intervals that you are making work, in the long run.
But from a practical perspective, people do see, interpretation, people use the same interpretation for confidence interval.
Yes.
That technically it is not correct, because the reason it's not correct because of the definition of the probability. That's why when we early on say the definition of probability have these long-lasting ramifications for that reason. But in practice, people do use it. To do an inference, yep. and often exactly. That works just fine. That's just. That's it.
Yeah. Yeah, Fang and Jose, there's a couple of questions. Can I pose those now, or would you care to wait?
Sure.
Well,
let's see if they're quick questions.
If they're quick questions, yes. So yes, go. If and related to this, yes, go ahead.
The first one, Bayesian methods can still be evaluated with frequentist properties. Is that correct?
Yes, you can say that. That people do say that if what would happen to the credible interval if we were to repeat the experiment many times over, and I think this is called long-run frequency coverage, and this is something that FDA is very interested in to evaluate the coverage probability in the scenario. If you do Bayesian, but assuming you were to do this in many times over. Yeah. Yes.
There's some little things here in terms of choosing the priors. I will touch upon that.
Yeah. A second related concept to that would be Bayesian type 1, type 2, and power for that way of thinking. Yes.
A second question is, if the inference from the Bayesian analysis is something about theta, and theta is a model parameter, you stated that they're not concerned with future observations. So then what do they use this model parameter for if it's not to predict future observations?
To clarify, not concerning of future observations is when I infer about the parameter theta, I do not assume what type of data that I will see in the future. I see 17 observations. I make my inference about parameter based on the 17 observation alone, without assuming what the behavior or the distribution assumption of anything in the future. But I can still make prediction if I have the model, what I know what the theta is, I can still predict what the future might be.
Correct.
Yeah.
And the other thing that we can, I'm sorry, we're going to add it, and we'll get into this with the examples. Another thing that I really like about the Bayesian methodology is the predictive distribution. So you can actually predict data, not just the data based on the analysis, and we see how that is used. Yes, one more, and then we'll keep going. We're going to have a Q&A section. We're going to have a Q&A session at the end. So.
Right. Which interval is preferred?
Oh, you mean between the HPD and the equal tail interval?
And the equal tail.
I think that's what he means, yeah.
So
yes.
Most frequently people like to use HPD because that's the smallest region where the most of the probability is concentrated on. But HPD intervals themselves are not invariant to transformation. So
yes.
like if you have HPD on theta, you can't just you can't square root, and you want to infer on the square root of theta, your HPD doesn't just carry over. But that's when if you are concerned with equal tail, and then they are invariant to transformation. I personally use HPD because we mostly are comfortable with it.
Yeah. But again, that point about transformation is important because sometimes in practice, you may get an interval for the variance, and then you just take the square root of the limits to get an interval for the standard deviation. But as Fang said, if you have a credible interval, you're okay. But if you have an HPD interval, you're not okay. Means you have to redo your analysis, generate an interval for the standard deviation rather than the variance. So, and these are some of the things that you learn, the little tricks as you go along. But it's a very important question, So in terms of the choice of prior, we normally bucket that into two categories: a diffuse or non-informative prior. Flat, as Professor Gelman says, lets the data speak. Or you can have an informative prior that is not dominated by the likelihood. Likelihood, we mean the data, and it has an impact on the posterior distribution. And this is going to be important when we get into some of the examples, is the use of prior knowledge, okay? Again, this is where, we get suspicious about the prior because, I can have a prior and Fang can have a prior, Stan can have a prior, and we may get different results because we're all using different priors. And as a frequentist, we may believe, oh, well, we're biasing the results depending on how you choose the prior. And that could be true, but this is important to keep in mind.
This is an unfortunate use of a name, and I think the name of informative prior makes people suspicious that you might be injecting too much information per se. The Bayesian themselves are sort of at a not in agreement with this neither. One side really thinks that we need to be non-informative, just meaning that we don't bring in too much personal opinions into analysis. The difficult thing is there is no such thing called non-informative prior. They might look non-informative, but they are not non-informative, especially say if you are flat in one parameter space, transformation can look very, very informative. The other side of the criticism of the informative prior is it's potentially open to abuse, but the informative prior can, even within the Bayesian, to say that this is just the way nature of analysis is. We each bring information.
But wait, there is more. Even the Bayesians, as Fang is saying,
the Bayesians
they're
still
uncomfortable with
disagree
that.
with that. Not everyone agree.
So you have Professor Gelman, for example, another famous Bayesian, and they're talk about weakly informative priors. They want to use the information, but we're going to use information, but we're going to include less information that we actually have. And I think the intent here is to ameliorate that suspicion and that bias. But, you know, as Fan said, it's a very difficult thing to do, okay? Because it's hard to express a prior belief totally
the key is most people are comfortable expressing a prior on what you know. But the requirement sometimes is you got to be able to express prior on things that you don't know about parameter. And that is a tricky part.
Yeah.
And because you don't do that, not everything is non-informative in that sense.
Exactly. And we'll talk about these things when we get into the examples next week. So again, the prior is subjective. Again, remember the likelihood, again, is still subjective because you're selecting a normal distribution, but it can be another distribution. Degree of belief, remember we discussed that. So some people talk about subjective based, other people talk about objective based. And what the emphasis I'm going to put in here is the prior knowledge. And this is where I think people in the industry, especially in biotech, we have an advantage because we do have this prior knowledge. Okay, so the prior knowledge here that we're talking about is like product. So if we're doing some type of inference of a new molecule, we already have a history. You know, we're in business for maybe 20, 30, 40 years, some companies, and we have some like products that we can use. And also across different companies, we don't share that information, but if there was a way of doing that, then we can use it. So we do have that prior knowledge, and it's science-based. It's a lot of science and engineering knowledge, and it's something that can be vetted by the subject matter expert. It's still subjective, you know, we call that trained subjectivity, or I like this, McGill has a classification of objectivity into 4 categories, and one of the ones that he talked about is disciplinary objectivity. It's an objectivity that means it's a consensus among experts, and that's what we have in science, because that consensus changes if you have new findings. So, and not only in medicine, but in engineering, in physics, and all that. So, but we do have that in biotech, and we're going to show you how we use that prior information in some of our examples later on in weeks 3 and 4. But just remember, there's always tension between objectivity and subjectivity. We're all subjective, and we find ways of creating that objectivity, for example, like the disciplinary objectivity there. And the person that asked that question about using frequentist methods to do that, well, Professor Boggs talked about that. And remember, Fang has been using the word sampling distribution, not frequentist. And Professor Boggs, in his paper in 1980, he talked about sampling and based inference. Okay, and he saw that as complementary. And one of the things that he proposed is if we can use the data we have to test certain aspects of the prior. Okay? And I think that may help answer that question that someone was having about frequentist. So some of the advantages and disadvantages of Bayesian methods. It's a principal way of combining the prior information with the data that we have. Inferences that are exact. Fang already talked about the confidence intervals and their interpretation, the Bayesian intervals. You can actually say that the probability is 95% that your parameter is going to be within that interval. That has complete sense in the Bayesian point of view.
And by exact, what we mean is that the shape of the posterior distribution, however skewed or different shape is, it is exact. It's a functional form. It's not based on asymptotics. That's what we mean by of the posterior distribution.
Exactly, or approximation. And for example, and we'll show you this when we give you examples of comparability. The t-test under unequal variance is as an approximation because we don't know what the distribution is. But using Bayesian methodology, we can derive the posterior distribution of effect size, for example, and it's no problem. We can make inference using that posterior distribution. So that's absolutely not an issue, the Behrens-Fishler problem there. And as we've been saying, the answers are totally interpretable in the sense that it means what it means. Some of the disadvantages, okay, well, it doesn't tell you how to choose a prior, but we're going to discuss some of these aspects and how we can do that within CMC. And heavily influenced by the prior, and this is again where we can use some of the frequentist ideas and where we can do some sort of quote unquote sensitivity analysis and see how that influence the data. But the priors that we are suggesting within the CMC biotech context are the discipline objectivity, are the ones based on prior scientific knowledge that is vetted by SMEs.
Yeah, just to add on these 2 points that Jose just said, is that not only the Bayesian doesn't tell you how to select a prior, it requires you must select a prior. So from a practitioner, sometimes people throw up their hand, they say, I don't really know what to do because I have no opinions and I don't know what's the proper way of expressing. I have no preference on certain prior distribution. But unfortunately, that is a requirement. You must do that. In the second point is, so an obvious sort of extension of this criticism of producing posterior that can be heavily influenced by the prior is that it boils down to an exchange of opinions. Why don't you tell me what you think? I tell you what I think, and we call it a day. Unfortunately, the reality of the things, that's usually how it works. And when we look at what's going on in the world, but just because you could do that doesn't mean that every Bayesian inference is done that way. It's just a exchange of prior opinion without any substantial from data. And the way that the Bayesian are doing is that, yes, we could disagree, but if the data changed, our opinions should change. And that's where the data information comes in, that even if we have very different opinions on something, the more and more data that come in, we would become more and more agree with each other, and our opinions would change based on the data. So Bayesian just reflecting this way of thinking.
And I think one thing that is important here, and Stan was asking us at the beginning in terms of validating some of these things for the agencies and all that, for us it's very important to be really transparent, and this is a point that Professor Gelman also emphasizes, is to be transparent as the choice of prior and why you chose that prior to and the information that you used to choose the prior. That's important. The last bullet there also relates to that. Since this is Monte Carlo simulation, you can get different answers unless you use the same random seed, and this is another way of generating, quote unquote, the same results. So if we envision that if this is used in practice for submissions and all that, then the seed is also important in the analysis. So you have the transparency in the prior, all the choices that were done, and the information that was used to choose the prior, so you can have the discussion with the agencies as to how it was done, and also in order to be able to reproduce the results. This is a minor thing there, but it's important to keep in mind. So some of the examples, we're getting to the top of the hour, that we're going to be talking about in the next parts of this webinar, that we deal a lot in CMC, is setting acceptance criteria in various situations. For that, a lot of you use tolerance intervals, tolerance bounds, and they're commonly used to set acceptance criteria, to check limits. So if you have a level that you have to meet, for example, for lead in air, you may compute an upper bound, an upper tolerance bound, and compare that to that level. And if it's below, then you can see it's okay. Sometimes the tolerance bounds are used to set a specification or as a starting point for a specification, and sometimes they're used as a surrogate for fitness for use. But all of these tolerance bounds should be based on a distribution that adequately describes the data. Not everything is normal. I challenge that assumption all the time. That's one of my pet peeves, that in industry is rare when something is normally can be approximated by a normal distribution. So I asked, so for the frequentist point of view, we have some solutions. If the data is normal, we have some exact tolerance bounds, one-sided and two-sided. If you have a normal distribution, because of the relationship, you can take the log of the data, compute your normal base tolerance intervals, and transform back, and those are exact. For gamma distribution, amazingly enough, the cube root transformation works, but it's an approximation. For a Poisson, there is a closed form approximation by Krishnamurthy. And Krishnamurthy, and I think Martin is the other author, Matthew, I'm sorry, Krishnamurthy and Matthew, they have a book that I use a lot where they deal with all types of tolerance intervals within the frequentist approach. And you'll find the cubic root transformation for the gamma. But what about the rest? What about if you have viability data or yield data or size exclusion or impurities? This is data that is bounded between 0 and 1. So that, if you look at it, a normal is not a good approximation. Normal goes from infinity, minus infinity to infinity. So this is, in my experience, better approximated by beta 0 and 1. What about count data? Subvisible particles. Poisson, negative binomial. What about positive quantities like forces? You have the Weibull, the log logistic, the Frechet, log normal. There's some approximation for the Weibull and the log logistics, but again, they're approximate. Remember, in the Bayesian framework, we have not approximation, but exact results. So we have to keep that in mind when we do our data analysis. I mentioned that's a pet peeve of mine. I did a lot of work in reliability, and I always tell people that in reliability, the normal distribution is not that normal. I think the only example where you can use a normal approximation is to describe the life of filaments in light bulbs. But everything is going LED, so that example is not going to work anymore. You know, so a lot of you know that within CMC, the data that we work with cannot be approximated well by a normal distribution. And we'll show you some examples. And this is what I'll talk about, the power and flexibility of this Bayesian framework to deal with this. What if you have a model? You have to deal with variance components. From the frequentist point of view, some of you are familiar with the Hoffman and Kringle approach that allows you to compute a tolerance interval if you have a variance component. But this is not a true variance component methodology. It's more an effective sample size methodology that is used to adjust the limits. From the Bayesian point of view, you can just specify any model you may have and get tolerance bounds for that particular model. If you have linear models, the stability data, we'll be dealing with that. We'll show that. If you have something more complicated, it's a generalized mixed model with random coefficients and data that is not normal, Poisson, for example, negative binomial beta, you can handle all that. It's a little more complex in terms of the specifications, but the methodology can handle it. So just as you all know well, it's not just a set of data. There's some structure and context that we have to bring into the picture when we select the models and techniques that we're going to use for the analysis. Apart from the Bayesian and the priors, this also holds true for the frequentist approach. Evaluating comparability, we do this a lot. For example, if we're dealing with equivalence tests, we want to show that the biosimilar is somehow comparable to the reference from the analytical point of view. This is mostly done comparing means. There you have an equivalent acceptance criteria. Those are the red lines in this plot. And then you have the dot is the estimate of the difference in mean, and that is the 90% confidence interval. That's the one two-sided t-test or the TOES for that. But several people have mentioned that we have issues with that because when we do that, there are unequal variances. The acceptance criteria was prescribed by the FDA a while back, even though they have withdrawn that guidance. The acceptance criteria depended on the standard deviation of the reference product. And the test also depends on the standard deviation of the reference. So Rick Burden and I, in a presentation, DIA, talked about this. And Rick Burdick, he has a great paper on analytical comparability, just came out in 2017. And he actually they won the STAN award at the non-clinical biostatistics conference in June. But from the Bayesian point of view, what we're going to look is at the posterior distribution. You can see there the red distribution and the blue, those are the posterior distribution for the reference product and the biosimilar. So you can see that in terms of this location, the center, you can make the case, well, yeah, maybe the centers are similar, but you can see one distribution is fatter than the other, meaning it has more dispersion. So we'll talk about ways of looking at all those dimensions. Pre and post change, familiar with that? So we do lot release. We may compare slopes of the pre and post change. We can use some means comparison for characterization methods, but we have those type of comparisons that are similar to the biosimilars and inherit some of the same issues here. Method bridging, notice we have two dimensions. We want to compare the means, but we also have to compare the precision of the two methods. We want to estimate the bias to show that the new method is not biased with respect to the old one. And for that, and we'll go into these details when we talk about biosimilars, we're talking about a four panel of Bayesian posterior distribution. This one here is the mean difference, so this is the posterior distribution of the mean difference. This is the posterior distribution of the variance ratio. This is the posterior distribution of the effect size, or the variance-Fisher problem. Again, we get an exact posterior distribution that we can use for inferences. And then here on this side is the total variation distance between the two distributions. Again, you can use some other things, but that is another way of measuring how close the distributions are, because we not only want to see that the means are close in some sense, but we want to see that the standard deviations are close in some sense, that the effect size is close to 1 in some sense, and the distributions overall are close. So we'll show you some examples of that when we look at some biosimilar data. A problem that some of you may have, I've encountered this several times, someone may come to you and says, hey, we have a sample that shows contamination. Now what? We have an inventory of vials. Now what we're gonna do? Can we help us? Can you tell us what the prevalence is of the contamination inventory if we have the sample size of 1? No. Can we take more samples to get a better estimate? How many samples do we need to take from inventory? What do we do if we grab a sample of 10 and we see no defects? Can we go ahead and say, okay, the inventory is good? What if we see 1 defect? Do we panic? Because now we have 2 defects or 2 contaminations. What if we have prevalence information from the supplier, from other samples, the prior knowledge? And this is what we're talking about. So part of this, and we're going to be looking at this in part 3 of the webinar, is the use of historical information, prior knowledge. What if you have something like that? You have a new product and you only have 4 samples. This is visible particles, and they're asking you to set an upper bound for that new product. You know that even if you had a frequentist approach to do an upper bound based on the Poisson or negative binomial, that limit is going to be really high because it's going to reflect the uncertainty in your data because you only have 4 samples. But can we use information from similar products? Then we do some type of empirical base, and we put it in quotes because it's a little different from the traditional base. And we can also use hierarchical models, and we'll be using that as ways of combining this discipline objectivity, this prior knowledge that we may have. Another example, what if you have a new monoclonal antibody right there, and you want to set some expert limits for that? But this is limited data. There are only 7 lots there. There's lot-to-lot variation, and it's not normal data because this is some size exclusion. Again, can we use data from like maps? And in this case, we did have 4 like maps that you can see there, and they were vetted by the SMEs. So one thing that Fang and I did, and we're going to show you this example, and we're going to show you the code and all that, is to take these and use some type of power prior to combine that information. And we actually gave this presentation a few weeks ago at the nonclinical biostatistics conference, and that's the name of the talk there. And also a little PR here for Paul Thaya and Tony Hamad, that they got approval from Chapman Hall CRC Press, and they're going to be publishing a book on Bayesian applications in CMC, and that for me is big. And Fan and I are going to write a chapter for that book, and most likely it's going to be a chapter on this example. Okay, so why use Bayesian statistics? Because it allows to combine this prior knowledge into our analysis. So that's the Bayesian theorem there. The posterior is proportional to the likelihood times the prior. And the likelihood, that's our data distribution plus the model that we want to fit. Someone was asking about predicting with the model. You know, you can have something just as simple as estimating a mean, or you can have a stability model where you want to predict what your expert is and some limits. And that means just how likely is the data given the parameters that we have. We have a prior. In this case, this is what a flat prior looks like. And then if you combine those two, you get a posterior probability that's exact. And again, the inferences in Bayesian statistics are based on this. As we saw, you know, the posterior beliefs are proportional to or prior beliefs. And these are some references that are here for part one. And I love this quote from the discussion. And one of the things that for me strikes me in the old days, you know, in the 20th century, when people wrote papers like Professor Box and Cox, some of you may be familiar with that paper, Analysis Transformation. That paper has a frequentist solution, and at the same time, they show the Bayesian solution. So they did not shy away from showing both. So they did not partake in that controversy. But I was like this, that, you know, as I said, you know, I'm not a diehard Bayesian, Thang is. So now we're at the point we're going to switch gears here. And Fan is going to talk about PROC MCMC and PROC BGLIMM.
When we are switching, Stan, are there any show questions we can just answer quickly regarding the things that has been presented?
And again, we're gonna have a Q&A at the end. We're about 50 minutes.
Yeah, no new questions have come in, Fang.
Okay. Okay, so this part is to just give some high-level introduction to the two procedures that SAS has in providing Bayesian computation capabilities. I say high level, meaning that I won't spend much seeing time in the detail, as we will see some of the examples in the later parts of the of this whole tutorial. PROC MCMC and PROC BGLIMM. PROC MCMC is a general sampling procedure. A general is in the sense of it handles the model in the way that you see fit in most cases. Of course, it provides a flexible syntax in that sense. So when you use a procedure, you want to think how you write down a statistical model, and all aspects of it need to be specified. This is the price you pay for being generality. You have to say what are the parameters, what are the price distribution, what are random effects, how the random effects enter the model, what the sampling distribution and likely function on, so on and so forth. And then the procedure would generate posterior samples based on the model and the prior that you provide. When you think about the procedure, SAS's procedures are statement-driven. Statement-driven is in the sense of they provide coding experience and they make programming readable. So that's how I want to think about it. And for complexity, for things that are complicated, this is where the data step comes in. So a procedure is one of a few SAS procedures that wraps data step programming environment inside the procedure. You can fit many different models, which I won't go through many of them, but just to maybe see some of the examples of it. It supports data step, it supports your own sampling algorithm, functions, distributions, and it does predictions and so on and so forth. If you're not familiar with SAS, SAS input data set is just a rectangular structure that has variables on top and the records horizontally, and nothing particular, just ASCII file. Think that way, and missing data are used as a dot, and this is the type of input data set that a PROC MCMC procedure takes. And the important thing here is that the syntax reflects the model that you want to fit. And you can see that if I were to fit the linear regression, you can match each piece up here with each piece down here. What the model is, the normal, the transformation in mu, beta parameters, what the priors are, and so on. Of course, you can change your statistical model. You can change different prior, different likelihood, and then you can see that you can make corresponding changes based on what the standard support distributions at PROC MCMC.
And to add to this, if you remember that diagram that we show you of the Bayesian framework, that we have the likelihood for the data, and then we have another distribution for the prior. So we have two probability distributions that we deal with. So if you see in that syntax, you have two probability distributions for the beta naught and beta 1, and one for sigma. Those are the priors, and it's obvious there is prior. And the model there, the weight, that is the likelihood. So you have the two probability distributions that we deal with specified, And if you're familiar with SAS, this is very intuitive. If you're not familiar, it's a little intuitive because you use the word prior. That's how you define the probability distributions for that. And then PROC MCMC and the algorithms behind the scenes take care of the Bayes theorem behind the scenes to give you the posterior. So
yeah, that's what Markov chain Monte Carlo technique is being built behind it. Okay. Keep on going with it is because it supports data step syntax. So like if else logical control comes in play, you can for example do a change point regression and many other similar models. So the key point we want to emphasize is that there typically is a matching between the type of model that we'll want to fit and how you will write down. And so write down to be, but you have to know all the global details of the model that you have in order to use PROC MCMC.
Yeah, and before you go on, Frank, in that previous slide, we're going to show this when we use the prior information. Remember the example that I just showed you that has the stability data, and we have 4 maps that we're going to use as prior knowledge. So this helps a lot because each of the maps is going to give you a set of parameters that we're going to use. So it's the same syntax that you have here. Rather than height will be the molecule. If molecule 1, then you have these parameters. Molecule 2, you have these. So you can specify multiple moles there. Again, just showing you the flexibility of the procedure.
Right. Yeah. Thanks. It's all part of because of the data step capabilities in the procedure let you process the different model in different ways. So that's a key point to remember with it. It produces these posterior estimates. Of course, the most important thing is the posterior samples, which is saved to a data set you can use for inference. Then the usual suspect of the estimates and the convergence diagnostics and the graphical display is all that. One thing that I do want to emphasize is PROC MCMC relies on SAS programming language, just thinking data step. If you're going to program, the order matters. So if you say mu is equal to x times beta, and your model y is normal mu, this line mu better come before model. PROC MCMC will not detect out of order because it doesn't know what the real order is. So you want to remember programming order matters. And that also means you can reuse the same symbols in multiple programs. You can redefine mu to say y has a mu, and you redefine mu again, and your another response has another model, and a variety of things that you can do for that reason. So think about data step as the order matters in that. The second thing I want to talk about PROC MCMC is a distribution that it supports. So it supports on the larger scale of things, 2 types. One, the standard distribution, the building ones, and one, the general distribution, the distribution that's not standard that you want to program yourself. So in standard distribution, you have the univariate, multivariate, discrete, categorical, the usual suspect of things that's are all pretty much inclusive in here. This is just a sample of them, and univariate is on top and discrete, and then you have Dirichlet, inverse Wishart, multivariate, normal, multinomial, etc., and the discrete distribution, like categorical distribution. Usage of it is very simple, and so if you recall an early picture of we're gonna couple arbitrary prior and arbitrary likelihood to do Bayesian computation. This is where we hope that providing a wide suite of distributions enable you to make inference based on any arbitrary combinations of prior distributions and the sampling distributions in the likelihood for that. Okay. Some distribution, just to heads up, is you gotta specify what is that you mean. For example, normal has variance standard deviation precision. You have to tell the procedure. Do you mean precision or you mean inverse gamma? So this is an explicit requirement. You can't do normal 0, 1 because MCMC need to know what this one is. So there's a standard distribution has some trick in it, but by and large they are what they are. It also supports truncated distribution. Truncated distribution just means that my parameter is truncated at a certain range. It can be truncated by some value, or it can be truncated based on some other parameters in the model. Okay, so these syntax can also support, and again, you can embed programming statement inside a standard distribution for it.
And one thing to add, I'm sorry, Frank, one thing to add from the practitioner's point of view that I have learned is that parameterization is important. In Bayesian analysis, parameterization is important, and Frank just touched upon this. Just basically in how you specify the parameters of a distribution, if you specify the variance or the standard deviation or 1 over that. But we'll see later on when we get into the examples how you parameterize a distribution can help the convergence and things like that. So one thing to remember, parameterization is important. Just plant that seed in your head for now.
And the censoring is not the same as truncation. If you do sensor data is so PROC MCMC has its own way of handling sensor data. We call it C lower and C upper. So it's being truncated left sensor, right sensor, or interval censored. Depends on the type of model requirement that you have. So just to so you know that we support truncation and censoring for it.
And again, so, and again, this one is very, very helpful because you can do reliability type analysis within MCMC. That's the flexibility we're talking about. Normally, sensor data is the realm of reliability engineering, and you go to PROC reliability, for example. But we do have that type of data in CMC. That's LOD. Whenever you have an LOD, that's a sensor, left sensor data. And here, you know, again, the flexibility, not just of the Bayesian procedure, but the flexibility of the MCMC as a procedure, hats off to Fang, is that it allows to deal with all the different types of distributions that we may encounter. So, and we'll talk about that. We'll show some examples of LOD data later on.
And also supports multivariate distribution, but because of the legacy of the procedure, the multivariate distribution has to be array-based. SAS as a language is a symbol-based, symbol variable-based language. And in order to make something to be multidimensional, you have to declare them as arrays. So that's a step to always remember, to have a multivariate normal distribution. But it supports the inverse Wishart and so on and so forth. And then the other side of the spectrum is that if something you have that's not in one of the standard distribution, PROC MCMC also supports a way that you can use a programming statement to program your own distribution. So what internally what the function is called, there are two such functions, a general and degeneral, and D stand for discrete. And what the syntax is very simple. is you say prior or model of a random variable either follows a general L-like and degeneral LP, however the symbol, that name that you put in here, that doesn't, it's an expression. We call it expression. I like to put L in front of it to remind myself this needs to be the logarithm of the distribution. And this expression is, in fact, what you write down as your model. Here's just an example. In a general distribution, suppose you want to do a prior that's 1 over sigma square. It's a non-standard distribution, and no such a thing this is a prior, has this shape. So what you do is you take the log of it, and it's negative log of sigma square plus a normalizing constant, which we don't know. We know it doesn't exist here, so it can be discarded. This negative log of sigma 2 is going to be the expression that evaluates LP, conditioned on the sample of sigma 2, posterior sample, and that becomes the prior density on the logarithm scale for the parameter sigma 2. So just think of the density and take the log, write it out, and put that in LP, and then PROC MCMC will recognize that is a non-standard distribution and act accordingly. Okay, so as a sort of a basic thing to use a general non-standard distribution is to have a flat distribution, and you can use that as a trick to sample from a prior distribution to understand what the prior look like, because if you don't have any data, the prior is your posterior, and this is a trick to generate from prior to understand what's the impact of the prior. General 0 is the likelihood indicator of flat prior, and with no data, so that be it. Your posterior would just be a beta 3.2, and you can generate statistics knowing what the distribution looks like. You can visualize it, and etc. etc. And more interestingly, you can have a high dimensional distribution with many marginal distribution and a conditional distribution, and then you'll be able to see that if my normal distribution has a variance of S2, I know what the shape would look like if it's to be 2. But if my distribution of sig variance follows an uncertainty of some other distribution, what would the marginal distribution of mu look like? And you can use simulation to tell you this is what the implied prior distribution on mu if the uncertainty on the variance has a prior of quotient. Okay. Analytically, this is difficult, but through simulation, you can tell them right away. And this is a usage of what I mean by that. Okay.
Yeah, so now, so if you didn't know, this is a very nice trick that you can just, even if you're not a Bayesian, you can use PROC MCMC for simulations.
The simulation.
Now you know.
That. Yeah, to do this. Now moving on to BGLIMM. It stands for Bayesian Generalized Linear Mixed Effects Model, which is a procedure that's entirely dedicated to Bayesian analysis of this class of the model. You can think this is a close cousin to the GLIMM procedure. So just a bit terminology. Let's, instead of doing to the generalized linear mixed effects model, we start with SAS treatment of the mixed effects model. So SAS treatment of a mixed effects model is what we call y is equal to x beta plus z gamma, and with an epsilon. The beta is considered to be fixed effects, and a gamma is considered to be random effects. So z are the covariates for the random effects, and x are the covariates for the fixed effects. Okay. Of course, what's fixed and what's random can be open for debate, but for the moment, let's just assume that beta is the same parameter for all observations in the input data set, and a gamma reflects a cluster structure. So you have hospitals, you have schools, you have different classroom, and each have different effects. So that's considered to be random effects. Two strong assumption in a normal linear mixed effects model is the random effects assumed to be normally distributed centered at 0 with covariance matrix G, and epsilon is assumed to be normal with variance covariance matrix R. In SAS terminology, we call the G as a G-side matrix and R the residual side of the residual covariance of the residual. So you think of this picture, the G is defined in the random statement, R is defined in the repeated statement. So these are the four chunk of parameters that a mixed effects model has: the beta, the gamma, the G, and R. And of course, you can have a gazillion number of them. They can have very high dimension. And the extension to the generalized linear model is fairly straightforward. You have a linear predictor, you have a link function, you have a response distribution that's in the exponential family, makes a generalized linear mixed effects model. And this is what the Bayesian treatment of that is what PROC BGLIMM does. So the mixed modeling procedure in SAS, you think of the picture is the following, just to tell you where we are. In the classical statistics, we handle exponential family is used in GenMod and mixed model, PROC mixed, with random effects. You put two and two together, you get GLIMM mixed, and if you want to extend to nonlinearity, you go to NL mixed. If you want to do Bayesian, the GenMod has a base statement that uses the same procedure that can do Bayesian analysis of exponential family. The BGLIMM shares syntax with the mixed and the GLIMM mixed that handles the generalized linear version of both mixed and GLIMM mixed procedure models. And then MCMC is a cousin to NL mixed. That's our programming based for this. So BGLIMM is here. It is less general than MCMC, but the convenience makes things easier in many situations.
Yeah. And then again, this is a practitioner commenting, and that's the key word, the convenience. You can do all these mixed effects models in PROC MCMC, but it's a bear. You know, keeping track of all that. I mean, it's not easy.
The programming
Exactly.
burden is much higher using
Yes.
PROC MCMC. But if you have a similar program, then programming burden for BGLIMM mix is much easier for that.
Exactly, and that's the nice gives that you're giving us there with BGLIMM in a way, and we'll show an example of that. The convenience.
Yes, and just to think that the difference between using a BGLIMM procedure and a GLIMM mix is that in the BGLIMM you have to specify prior on the beta, the fixed effects beta, the G side covariance matrix, the R side residual covariance matrix. The random effects is assumed to be normal distributed center 0 with covariance matrix G, and that's the same with GLIMM mix and BGLIMM too. And what PROC BGLIMM does is it just samples posterior distribution from all four joint 1000-dimensional parameter space and use Monte Carlo for it. Okay. So the essential statement, PROC BGLIMM is statement driven. You can't program in it. You can't specifically use this data step to programming little things in there. It's not, the capability is not there yet. So the essential statements are the model, the random, the repeats, which specify what the Y, the X, your fixed effects model, what the random covariance Z, the G side covariance structure, and then if you have repeated statement, then you have the residual side of covariance matrix. It handles a class statement that PROC MCMC does not have, which to people is actually important if you do class variable, and you can do post estimation, sampling estimate inference, use the estimate statement that computes a linear combination of parameters. So it's a fairly simple procedure. The model, the random, the repeats does the bulk of the work in such a things. I am going to just give you a quick example of a logistic random effects model and perhaps do repeat measurements. And I think we are doing okay on time. Again, this is a fairly high level introduction. So the example one is a logistic regression with random intercept. The data is it comes from 15 different centers. And we want to investigate 2 medical procedures. So in the input data set, to the right, multi-center, you have a center input 1 through 15 and 1 through 15. The group is indicated as either group A or group B, who received 2 different type of treatments. The side effects is, or the N, the third column is the number of patients who received that given the procedure, and the side effects is the name of the number of patients who reported side effects. So it's a very simple data set. We're going to model a normal binomial model, because we're going to sample the proportion, the binomial ratio. We have a fixed effects as a group, and the random effects is center. Okay. So you can see that when you run the procedure, the expectance of the input data set, how long you want to run the MCMC chain for 10,000, you want to thin that by 2, you have a random seed that repeats, ensures the repeatability of analysis. You save the posterior to an output data set, that's a posterior samples, and you say, I'm going to ask to plot all these diagnostic plots. There are 2 categorical variables: the center indicator variable, which is a subject variable in the random statement, and then a model statement has a group covariate, which is a fixed effects. So the group is, I'm sorry, 2 treatment of groups. The group is here, that it's a treatment group of A and B. And the ratio of side effect over N does a probability, and by default is a binomial model if N is not 1, and with a link function of logit with it. So here is the BGLIMM output. If you use SAS, it's a typical model information table, tell you what the distribution, the link, the fixed effects, random effects, what sampling distribution is being used, simulation details, and the number of threads, which is 1. If you have a larger problem, the procedure is multi-threaded, and you can increase the number of threads to significantly increase, help with the speed of the thing. Also provides a class levelization problem and how many observations has been used. Because it's a binomial data, it tells you how many events out of how many trials. This is total N over, total side effects out of total N. And it produces, then it does 5,000 draw, it does 10,000 draw because you thin it by 2, it keeps 5,000 posterior sample, it estimates the posterior mean of group A and group P. Oh, sorry, go back to here. The no intersect means there's no beta 0 in here. So there's no intersect, and that's why you don't see intercept parameter estimates. And then the random var is the G-side variance parameter for the random effects, the center-wise random effects. So it's a group A and a group B, and the random var measures variability of center level intercepts. This posterior summary statistics has only model parameter, the fixed effects and the G side and R side. It doesn't have random effects estimates. You can request it, but random effects typically tend to be a lot, like can be in the thousands and thousands. So we don't output them by default. And they're typically not of inferential interest or focus anyway. It produces these trace plots, autocorrelation plot, and the marginal posterior distribution of all the parameters. In here, it's just group A. I don't think I have a group B in there, but it produces a density estimation, and you can compute quantities as it was you fit. And you can then use the estimate statement. So for example, to compute the log of odds ratio between A and B, you sort of need to know how the estimate statement works, but the log of odds ratio computes it is a -0.05 between the group 1 and group A and group B in this particular case. You can also compute functions of parameter. This is part of a Bayesian advantage of Bayesian analysis. Is once you've done your MCMC, get your posterior estimates out of it, you get transformation or functionals of these parameters for free. You don't need to worry about central limit theorem. You don't need to plug in. You don't need to worry about delta methods. You have a parameter, a quantity that's any functions of parameter of your beta B and beta A, for example, over two groups. You can compute the transformation for every posterior sample of beta B and beta A. Then you get a distribution of the quantity of what you want, okay, without having this. So this is really only computation per se, without having to do any paper and the pen type of work. So in this case, you can compute the probability difference. Okay, sorry, going backwards one time. It's the same concept similarly as a functional of parameter in the estimate statement. Except in the estimate statement, it only does the linear combination, the x betas. Okay? So if you want to do anything beyond the linear combination, you need to do it in the data step. And that's why there's this data step called here. You set the posterior sample or center out, and you compute the probability of differences. And then there is also a macro that computes the posterior interval and then the posterior mean and standard deviation of the distribution of the quantity that you want.
Yeah. And I was gonna ask about that. So one thing here, we're gonna be using this trick when we're generating acceptance criteria. We're gonna be using the quantiles of the posterior distribution. So we're gonna use this trick to compute the quantiles. And these macro, I mean, there's several macros there for post-processing, and I'm glad that you mentioned that.
Yeah. Right, and this, so this is now sort of in a way why people find it to be friendly to use Bayesian computation, because you get a posterior distribution on your quantity, any quantity. So if you have what they call a scientific question, I want to know the probability difference, you do a transformation, you apply them to every posterior sample, you get a distribution on the probability of difference between N2 and B, and then you can ask a question, what is the probability that the difference of probability is greater than 0? What's the probability that the difference of probability is greater than 0.1? And by that, you essentially just count the proportion of the sample that's within the region you want. It's a cumulative probability. Because of the samples, this is all doable. And in this example, the probability of that the difference is greater than 0 is greater than 99%. Okay, so this measures a direct confidence of the thing that you want to look at. Okay, and I truly think that this is what in a way saves sort of not save but enhance the Bayesian capability because of this convenience, and this is why also people are willing to put up with PROC MCM, not PROC MCMC, but by Markov chain Monte Carlo in general, because of the easy to inference once the sampling is done. You can do all sorts of inference, and it comes at almost no cost for it. The next example I want to give, actually, maybe we should just stop to see if there are any questions, because this is coming to 12:45 now.
Yeah, we should entertain questions. Let me grab back the.
Because we were running a bit behind.
Yeah, so. but we're going to be covering a lot of examples in the following weeks. So yeah, let's tackle some questions. If we don't have a lot of questions, so we can come back to this.
Yeah. So Fang and Jose, the first question is, shall truncation be applied to prior or on the likelihood?
should apply on
the truncation? Should it be applied to the prior distribution or to the likelihood?
prior? I would say on the prior, because if you already see the data, I mean, data is data. But truncation implies the things that you will not observe. So I would think that most typically indicates in the prior distribution to say that my variance is got to be greater than 0. I mean, it's inverse gamma prior, but it's truncated as 0. So if my p has to be between 2 values, and that will be truncation to indicate that I haven't observed something, but if I were to observe it, it got to be within that range, and that's truncation. But if you have your data, the data has already come out. You can say that, well, my data could also be a truncated, coming from a truncated likelihood. That's possible. But just indicates the nature of the data. Like my data has to be some CMC data has to be positive. The measure has to be positive, then it needs to be a positive likelihood. So that could also work.
Yeah.
That comes. Yeah, I was just going to add that is possible, as Fang is saying, and you have to remember I mentioned the structure and the context of the data. So we need always to ask the question, what is the data generating mechanism? And in some studies for forces and things like that you may not be able to observe a phenomenon, so it's truncated. And Frank did a good job explaining the difference between sensor and truncation. So it is possible to have that in the model too. And again, the flexibility is there.
Yeah. So the follow-up to that is that even if I think this is what the question is, even with if the prior is defined in a truncated way, you can still get data outside the limit.
Oh, if the prior is on a parameter, the parameter can truncate in all you want to truncate. That doesn't mean that the data need to be truncated. It might limit what the data would look like. Like if, for example, if you truncate your variance to be between 1 and 2, and your data is normal, centered at mean of 0 and the variance, and that will in effect limit what type of data you could possibly see. That's possible. So you don't want to be overly constrained of your prior, because it constrains the overall fitness. In this case, the fitness of the data. Because if you have data that's in the thousands and thousands range, and you say my variance has only to be between 1 and 2, and my mean is around 0, then you ended up having a very badly fitted model.
Yeah. And this is again goes into the discussion of the prior affecting the posterior, so as far as that discussion of how to choose the prior.
But I don't know if that also was that the question of concerning, whether the impact of the truncation on the prior would impact what the data would look like. Is that what I was trying to address?
Yeah, it's hard to say, but that's the way I interpreted it, Fang. Okay, the next question is.
No, I'm just saying in the Bayesian framework, we talk about the posterior. So the data is the data. We have that. So we can truncate the prior, and when we combine the prior with the data, then the posterior, which is what we're going to use to make inferences, may be affected by the truncation on the prior.
Yeah. Because your posterior, if you have a prior, say my variance is between 1 and 2, your posterior will be between 1 and 2. Your posterior of your sigma square will be between 1 and 2. The question is the shape, whether your prior could be flat between 0 and 1 and 2, but your posterior could concentrate it around 1.3 with a very small standard deviation. That's possible.
Yeah.
Next question. How do you evaluate the plots from BGLIMM, and when do they look good?
So
they're probably talking about the diagnostics plots.
Yeah,
and we'll talk a little bit about that.
There's this thing called diagnostics. I think it's a good thing that we convergence diagnostics. So in general, this concerns the concept of convergence, which I won't talk about it. Convergence Yes, I do need to talk about this because it matters. Markov chain Monte Carlo. You should think of Markov chain Monte Carlo, all these Bayesian things, as random number generator. A random number generator is going to generate from a high dimensional joint distribution that's defined by your model. Okay, your beta, your gamma, your G, and your R. And what exactly does that mean to be generating from that dimension? Is it's called sampling by proportion, sampling according to the density that the posterior specifies. In the high density area, you need to sample more. In the low density area, you need to sample less. The ratio, it should just be proportional to the height of the density. Think about that. And if you can't do that, then the whole bet is off. You can't generate a badly random number generator from a distribution that's you don't sample by proportion, that you can't use the sample to do your estimation. Okay. So now the question is, well, if I knew what the proportion need to be, I don't need the sample. Okay. But it doesn't answer the question. If I have the sample, can I tell, am I sampling by proportion? This is a question is almost similar to numerical convergence in optimization problem. Is if I knew what the MLE is, I don't need optimizer, but your optimizer has stopped, am I at the MLE? It's a similar thing. So in MCMC, there's always this question on convergence. Convergence just means how fast I'm going toward the high density area, and then am I sampling by proportion? Okay. Unfortunately, there are no definitive tests on convergence. Just don't know how to do it. For precise reason, I don't know what the true proportion to do. So we sort of rely on this. Well, if it looks good, if it doesn't look good, we know it's bad. If it looks good, we have a higher chance of getting it right. Okay, so we are at that stage, and that's what I mean by no definitive test of convergence. We can check different aspects. We think what a good convergence should look like. If it doesn't have that, we know it's definitely not good. But just because it looks good doesn't guarantee it will be good. Okay.
That's right. And from the frequentist point of view, before you talk about the graphs, you can imagine if you fit in GLIMM model or nonlinear model using NL mix, for example, or even NLin, you have to deal with those issues of convergence. Sometimes it may not converge, and sometimes that may be due to how the likelihood function is for that particular data set that maybe has some weird edges. So as Fang had in that slide, we really don't know if we have reached a global maximum. So this is not just intrinsic to
it's intrinsic to all numerical problems, all statistical.
Exactly, as you have in that. So
using this, but it is an important feature. It is an important thing that you have to somewhat pay attention to.
Correct.
And now through sort of, I mean, this is endless because you can't truly by the end of the day finding what I need to do. So from a practical perspective, the two things that you typically look at it is that, you know, your marginal density is typically smooth unimodal, and that shape is a comforting thing, and there's this thing called trace plot. The trace plot is you concatenate the sample of your posterior jaw over time, and you look at it. Okay, you look at it, and when you look by looking at it is, if it looks horizontally flat with things to the whisk, that generally considered to be good. Okay. And if your chain is moving from somewhere to somewhere and it stabilizes, by stable it just means it goes flat, then it means you just probably need to chop off the front and you are good. If you have a trace plot look like this shape, then becomes non-convergence. And sort of the most perplexing thing is, what if you have something look like this? Okay, you look like this. What do you do? I'm not going to talk. I mean, there this discussion is that you can thin it. You can do this. So I don't need to, because it's just time now. But to answer the question, if I have a trace plot, I mean, it's now you can think that I'm hesitant to tell you because it looks very subjective. All right, it looks very subjective. The what's considered to be a good trace plot or what considered to be an unacceptable trace plot might be different from person to person. Right? So fast forward this thing. Let's skip all this thing, thinning thing. What I think would help is to numerically quantify the sense of mixing, and the concept of that is effective sample size. Okay. What effective sample size is the Markov chain sample size that's divided by summation of significant correlation. So if we go back to the to this BGLIMM example, I'm sorry. In this logistic example, I have 10,000 samples right here. And I know that because it's a Markov chain, that the sampling of them depending on each other, that there is autocorrelation. The effective sample size is I use 10,000 divided by the total sum of significant correlation. So that's the concept of this thing. It numerically quantifies how good of mixing that your sample, your Markov chain is. And you say, hey, what is a good indication of what's a rule of thumb to get this effective sample size? Typically it's 1,000. I was saying that if you get 1,000 effective sample size, it provides a good estimation in many situations. Okay, so it's a long-winded answer to your question. Is you can either look at the trace plot by looking at many trace plots, which you can say that this is acceptable. It stabilizes in the middle, it goes to the tail and come back. It provides a smooth unimodal marginal estimation of group A. Has some correlation, but correlation is really typically not an issue. And you can also look at effective sample size, and that provides sense of convergence. Yeah.
Is the percent sum int macro from SAS?
Oh, percent sum int macro, this is from SAS. This is in the autocall library. So what this does is the procedure computes the summary statistics by default. But once you exit out, in order to get it, you got to rerun the entire thing. Okay, in order to get the summary statistics. Or if you forgot to turn on the biodiagnostics or so on and so forth. So for everything that the procedure provides, there is a corresponding autocall. Autocall just means it's being released with SAS macro that computes the similarly quantified quantities. Yes.
Can you use informative prior than BGLIMM?
Yes, you can use informative prior in BGLIMM. The procedure supports a suite of prior on. Wait, when you say informative, you mean containing
can
information?
You specify the prior? Can you specify the prior, not use the default priors from?
Yes, you can. You can specify prior, and there's a few, but the prior choice is not as wide as available as PROC MCMC.
MCMC, that's right. Yeah.
What is
almost to the top of the hour.
But you can't do truncation and stuff like this, and that's
right.
Dependent prior on that.
What is exactly the thin equals 2 mean?
Thin equal to 2 just means that I have 10,000 samples. I have my Markov chain 10,000, and they produce a certain correlation. Okay, people don't like correlation too much, so I take every other sample. So I keep the first sample, the third sample, the fifth sample, the seventh sample. That's thin by 2, and I keep 5,000 of them, and the 5,000 of them typically has reduced autocorrelation than the original one. People find comfort in seeing a trace plot that has low autocorrelation.
No correlation.
And no correlation in the best. So for example, this is a picture, to think or not to think. This is a question. Is that if you have a trace plot like this, which typically look fine, but has very high autocorrelation, people find that to be bad. But in fact, it is not bad. It's just an indication of sampling inefficiency. It's not saying anything. The estimates is biased. You should not think that. So what people do is they thin it by a large margin, thin it by 10. So I keep the first sample, the 11th sample, the 21st sample, etc., and I get something like this, which has significantly reduced autocorrelation, and this is the effect of thinning.
Yeah, is there a default for thinning, and is there a recommended value for thinning?
The default is no thin. I would say the recommended value is also no thin, and the reason for that is the following. Okay. So the art of thinning, in the consequence of it is you can think that if I thin it by 10, this is thin it by 10, I have 500,000 and I'm thinning to 50,000. I don't know, some ridiculous number of it. Okay, sorry, 50,000. So I randomly select a subsample of 10% of it, and then I'm reducing it to here. Okay. So imagine that you can do it with any copies, and you have 10 copies of them. Okay, so you have 1 copy, 2 copies, 3 copies, and 10 copies. You throw away 9 copies and you say, I'm keeping 1 copy and using for estimation. But I can tell you that this copy is as good as any other copies of this thing, and all 9 other copies are all containing information that you can use to do the estimation. What the concern now is whether including these samples would hurt you, and the answer is no. I mean, there is a paper that that you can read about it, and the autocorrelation does not lead to biased Monte Carlo estimates. It's just simply an indication of poor sampling, and the reason is there is a Monte Carlo version of central limit theorem or similar to that. So this thing is not going to is not any worse than this in terms of Monte Carlo estimation. So the recommendation is, unless storage becomes a problem, you're better off keeping all the samples. You don't want to throw away. But that said, people do still like to have the practice of thinning. So we have this option called thin.
How many MCMC iterations do you recommend?
This is a question, go back to how I think it should be decided on the number of effective sample size. You should run the Markov chain, increase it so that effective sample size of all samples is roughly in the high hundreds of low thousands. This is what we recommend to people. And then there is, I do prefer using effective sample size. It's 101. I know we are coming to the end, but let me just finish this quick. I do think because smaller effective sample size indicates something is not right. A large number of effective sample size is typically good news. You can see that different trace plot have different effective sample size. This 20,000 chain, and this is ordered by the decreasing number of efficiency. You're becoming problematic in 20,000 chain, but has only 150 effective sample size. Something isn't quite right. And if you have very small ones, you have all different type of trouble. Okay, so I say that if you have a Markov chain that have a effective sample size in the thousands or even in the hundreds, if you're in the hundreds, you can let the chain run twice as long. You might get 1,000, and you'll be fine. You've explored the parameter space sufficiently in a stable chain to get proportionality. So that's kind of the idea.
Yep.
Okay. Oh, sorry. Go ahead, Jose.
No, I was just going to grab. I know we're at the end, past the time. I was just going to show one slide to tell you what to expect in the next three webinars. But if there's one more question, we can, while we do the switch, we can answer the question.
Let me switch back to you.
Are there any more questions, Stan?
No, that's it. Bernard sent a note saying thank you for a great talk, and I want to say thank you on behalf of the audience too.
Thank you so much for attending. So we have divided this into two parts. Part 2, we're going to talk about setting acceptance criteria in various situations, and we're going to talk about analytic comparability. Part 3, we'll talk about using prior knowledge. There are 3 more webinars, and the reason we have 3 is because we want to take our time going over these materials. We're going to discuss examples, the choice of priors, the results, the code. It will be annotated. So we'll see how it goes. You know, we may do part 2 in webinars 2 and 3, and then part 3 in webinar 4, or a mix of that. So, but it's just to give you an idea where we are going to talk about. We also going to make these materials available. So I'm working with the IQ to see what the best way to handle that is. But the slides that we have shown will be shared with you. Again, thank you all so much. Have a great weekend wherever you are, and I hope to see you all back here next Friday when we'll start talking about how to do this.
Have a good weekend, everyone.
Yeah, thank you very much. Thank you very much. Yep, bye.
Bye.
Thank you, everyone. Bye-bye.